Alright, I'm going to do the full limit process on these integrals now. Instead of just have an approximation, I'm going to do the whole limit and actually compute the integral. So, what I'm going to say is compute the integral from 0 to 16 f of x dx using right hand endpoints. Well, the way you do it, it will look a lot like what we did before. The first thing you're going to want to do, remember, we can break this up. We can partition this axis any way we want to. The best way to do it, I think, as far as ease of computation, is to do this. Choose one and only one delta x, and that will equal 16 minus 0, and it will be divided by n because we'll be varying n. N will be going to infinity. But this is how we always computed delta x in the past. And then if we're going to use right-hand endpoints, I don't think it's such a bad idea to have a picture of the graph and to see what those look like. Do you remember they came up like this? You hit the graph, you ran into the graph, and then you moved to the left to get a rectangle. And then this is the way it proceeded, something like this. Well, I don't care about the numbers or anything like that. I'm interested in more. Say I have something like an xi minus 1 and an xi. So I would be going to the right endpoint. Let's concern ourselves with this particular rectangle. And that'll allow me to get a formula for all of them. The width is always delta x. It's a smart idea to leave your widths all the same thickness. The height, remember, is the right-hand side, so it's f of xi. So, the area of this one particular rectangle is f of xi times delta x. And then if you do that for all n of the rectangles you'll inevitably be creating, you'll see that we have an I equals 1 to n, f of xi delta xi. How do you get these xi's? Well, if you look at them, the very first one at 0, this is considered x0, then this is considered x1, and this is considered x2, considered x3. So whatever you have for each of these, you start at 0, then you add a delta. Then you add a second delta to get to x2, then a third delta to get to x3. So if you want, this should be f of x0 plus delta xi, not delta sub xi, delta x times I times delta x. This is when we were computing just the rectangles. All right, well, x0 is 0. I'm going to write these in complete detail so you see what's going on here. I equals 1 to n, f of 0 plus delta x is 16 minus 0 over n, so it'll be 16 over n times I times delta x, which is 16 over n. And let me take it to its final form before I start going to the limit. We have f of 16 over n times I times 16 over n. And now I'm ready to plug that into the formula for f. Remember, f of x is negative x over 4. Remember, these are actual x values, so I can plug them into that. So I will have negative, now this will be my x, 16 over n times I divided by 4 plus 4 times 16 over n. Good idea here to simplify this and make it as easy on yourself as possible. So for instance, 16 over n times I can rewrite this as 16 over 4n times I. I like to have my I over there. Plus 4 times 16 over n. And now let me multiply through by the 16 over n. There's a lot of things you can do here. I think, but multiplying it through is not a bad idea, so let me go ahead and do that. That'll be the sum I equals 1 to n. So when I take and multiply the 16 over n times this first term, I will end up with negative 256 over 4n squared. Boy, am I very slow on the uptake, aren't I? If I have this 16 over 4n, before I even do this, I probably should have canceled here and made that into a 4. So let me go and take care of that. So I will have 4i times 16 over n. That will be 64 over n times I. And then plus 64 over n. And now I want to break these up. So I'm going to break it into negative 64 over n times I. N squared, plus the summation I equals 1 to n, 64 over n. Now keep in mind that if there's no I in it, it's considered a constant as far as this is concerned, because the variable here is I. And if that's not there, then I can factor that piece out. So I can put it the 64 over n, I equals 1 to n, of what was left as 1. Same thing here, I can pull out a negative 64 over n squared times the summation I equals 1 to n of just I. Now we can make use of some formulas that I had. If you'll remember, the formula for this one, negative 64 over n squared, the formula for 1 to n of I is the following. N times n plus 1 divided by 2. And the formula for just adding up a constant, 64 times n, is that constant times n, which in this case will just be n. Now I'm going to do as much simplifying as I can do. Like for instance, do you see how those n's cancel there? I can cancel this 2 in here and get a 32. I can cancel an n from here, and I'm left with negative 32. Now what I'm going to do is combine these two. I have negative 32 times n plus 1 over n, and then plus 64. That equals negative 32. Now watch what I do with this part right here. I'm going to break it into two fractions. One fraction will be n over n, and the other one will be 1 over n. And you'll get this, 1 plus 1 over n plus 64. Now what's going to happen, the integral from negative, what was the integral? Started at 0 and ended at 16. That equals that original sum we had, I equals 1 to n, and that was negative, what was the formula? I guess It really doesn't matter. I'm going to write the actual form. It would be negative xi over 4 plus 4. But each xi, that's what I want. Each xi was a (64 over n squared I). Plus 64 over n. I don't care which of these you use. And I must caution here, I made a mistake again. That integral is equal to the limit as n goes to infinity. And so all this we know equals this stuff up here. So we end up with the limit as n goes to infinity, negative 32 times 1 plus 1 over n plus 64. Constants, of course, are not affected by the limiting process. The only thing that's affected by the limiting process in here is this 1 over n, and that will go to 0. So this equals negative 32 times 1 plus 0 plus 64, and that equals 32. As we surmised yesterday, that was the exact answer because it's a flat rectangle. It's a triangle, so the formula for it's very simple. So anyways, there was the stepping through when we were using right-hand endpoints. Let me do this again for left-hand endpoints and then midpoints. I don't particularly like any of the other ones except right-hand endpoints, but the beauty of the midpoint is the most painful to do, but you also notice it is also usually the most accurate. So there's always seeming like you got to pay for something one way to get something some other way. So let me copy and grab another picture of this thing and we'll work on the left-hand endpoints. Okay, let's remind you what the function is. F of x equals negative x over 4 plus 4. That's on the interval from 0 to 16, the closed interval 0 to 16. We're now going to use the left-hand points, left-hand endpoints. So I urge you to draw the picture again and then see what left hand means. Remember, left hand means that our starting position is 0 here. So I draw a vertical line and then I would move it to the right until I got to, say, the next one. And then you would look and see where that intersected the graph, and you would draw another one. And once again, I'm really not that interested in drawing a bunch of these. I'm just interested in, say, getting to the point where I have xi minus 1 and xi. This time I'm going to have xi minus 1 to xi. I don't get rid of the whole thing, but that's alright. So, what is my thickness? If you leave all the thicknesses at delta x, you'll be in great shape. What is delta x? Delta x equals the right endpoint minus the left endpoint divided by n, and then we will let n go to infinity. The beauty of having these thicknesses all be the same is that if you let n go to infinity, you will not only get an infinite number of markings, division lines, so you get an infinite number of partition intervals, subintervals, but because it's got to be the same for every single one of them, you'll be forced to have the thicknesses going to 0 as n goes to infinity. So what's the height of this one? Well, this time it's f of x sub I minus 1. Now this is a little tricky here, so let's see what we can do. The right is the easiest one to number along. What we want to do is see what we have. Let's look at this rectangle. The area of this one rectangle is f of x sub I minus 1 times delta x. So then the sum of n of these rectangles is going to look like the following: f of x sub I minus 1 times delta x. How should I start my I? Well, I would begin my I at 1 and then go to n. Here's why. Because then if you have I minus 1 will start at 0, and then n will end at n minus 1, because here's what you're counting off. You're going to use this x value, which is x0, and then you're going to do x1, and then x2, xi minus 1. Eventually you'll get to the last spot. That spot is xn. That means the last spot, the last thing we're going to actually evaluate, is this interval xn minus 1 to xn. So when I get to n, that'll give me xn minus 1. Now you can correct this, but I can make this sub I, but then I start I at 0. So I could have, for example, I think I might end up doing this, because I told you starting at 0 is probably something you want to remember for that. Instead of this, I could look at the next one, x sub I plus 1. And note that I still have delta x as my thickness, but now the height of the rectangle is f of xi. Now, the area of this rectangle, so this is the guy here, is going to be f of xi times delta x. But now, because you want it to end at n minus 1 and model what we did on the previous problems, you can go from I equals 0 to n minus 1. It's going to be easier to plug this stuff in if you do leave it like that. So let's take a look at what is xi. Well, x1 is x0 plus delta x. Then x2, you add another delta x, then another delta x, and another delta x. So as before, we have something like this: I equals 0 to n minus 1, f of 0 plus delta x times I times delta x. This equals the sum I equals 0 to n minus 1. F of, now delta x we know is 16 over n. 16 over n times I. And I'll put the delta x again, 16 over n. Now let's go ahead and plug these numbers in. All this stuff goes in where x appears. So we'll have negative, we had x, 16 over n times I. I have that divided by n over 4. I think I put too much stuff in there. This was the x over 4 plus 4 times 16 over n. Let me go ahead and multiply it all out and fix this thing up while I'm there. I can cancel, for instance, make that into a 4, and this will turn into negative 4i over n. I like to strip out this stuff so that when I factor it out of the problem, I'll be able to use the formula for I. All right, 16 times the 4 will give us a negative 64 over n times I plus 64 over n. And then I'll be able to break this up and take these numbers out front in the following fashion. I'll have a negative 64 over n times the sum I equals 0 to n minus 1 of I plus 64 over n summation I equals 0 to n minus 1 of 1. Now when you use your formula, you got to remember I'm not doing the formula for n. This time I'm doing the formula for n minus 1. So I'll show you how that works. 64 over n times, it is this number times this number plus 1 divided by 2. Similarly, the other one is 64 over n, but it's not going to be times n this time. It's going to be times n minus 1, because I'm only going up to n minus 1. And I'm going to play a lot of the same games I did before. For instance, I'll take this out of there. There must be... There it is again. I'm just not completely with it there. I had an n squared here, so cancel one of those out. And then what I'm going to do is take a 2 out of here, 32. So I have negative 32. I'm going to do the same thing I did before, n minus 1 over n plus 64 times n minus 1 over n. Well, that's just the cutest thing, because if I wanted to, I could factor that stuff out, couldn't I? It really doesn't matter, but I'm going to do it. If I add these two together, I get 32 times n minus 1 over n, which I can write as 32 times 1 minus 1 over n. So that's the sum. So the limit as n goes to infinity is our integral. What I'd want on a test is this stuff right here. So let me go ahead and put this in there. Let me copy it and take it down. You have two parts. You've got the x part, and then you've got the delta x part. Both those are necessary for me to see. So we have the integral from 0 to 16 f of x dx equals, this is where I can put my sum, and it's not quite the sum that it's equal to the limit of that sum. So the limit as n goes to infinity, that equals the limit as n goes to infinity of this thing, 32 times 1 minus 1 over n. And then when I go ahead and multiply it through, I get 32 times 1 minus 0, which equals 32. All right, and now we'll move on to the most undesirable aspect, because it has the worst computation. F of x equals negative x over 4 plus 4. The interval we're working on is 0 to 16. This time we're going to do the midpoint method, or midpoint endpoints. Just midpoints. I don't know why they're not endpoints, they're midpoints. Precisely what they are, so midpoints. All right. Then, as we do before, if you want, starting at 0, then you have another one. Remember, the goal is you find the midpoint of that interval, and that's the height of the rectangle. And then you get another one, and you'd only go so high as the midpoint of the rectangle. So let's start our thing. I have an x sub I. This is probably going to be an x sub 1. That'll work. X sub 2. I think I can work this way then. X sub I minus 1 to an x sub I. And then the midpoint then would be directly in between them, about here. And let me draw a horizontal line indicating this rectangle here. Once again, I'm having trouble there. So the thickness is delta x, but what is this value? What is the midpoint? Well, the midpoint, MP, equals the average of these two numbers, x sub I minus 1 plus x sub I over 2. That is miserable, but that's what you got to use. The height, that's just the x value you got to use. So the height, I guess I'll put here, f of x sub I minus 1 plus x sub I over 2. That's the height, and the thickness is delta x. As usual, delta x equals 16 minus 0 over n. So let's throw these things in here. The area of this one particular rectangle is f of x sub I minus 1 plus x sub I over 2 times delta x. So let's take a look at x sub I. For when equals delta x times I, let's check it out. When I is 1, we'll have xi should be x1, which is true, because that'll be 16 over n times 1. That takes us to the next spot. Okay, then x2. Remember, I'm evaluating those things, but these things are what I need to get handles on. X sub 2. Then, so really x sub 1 is the right-hand endpoint to a rectangle. X sub 2 is the right-hand endpoint to a rectangle. These are like the x sub 2 stars, or whatever you want to call them. All right, so this equals 16 over n times I. Then x sub I minus 1 equals delta x times I minus 1. That equals 16 over n times I minus 1. Now let's add them together. 16 sub I plus 16 sub I minus 1, or they can be reversed, I really don't care. I'll have 16 over n times I plus 16 over n times I minus 1. And if I factor out a 16 over n, I'll have 16 over n times 2i minus 1. So it looks like odd multiples of 16 over n's then. Is that not true? And then if I want to get what's in between, then I will divide by 2. Divide by 2. So let me go ahead and multiply this through. This is 16 over ni minus 8 over n. So that's just the x values that we're going to plug in. So when we're doing summation I equals 1 to n, f of xi minus 1 plus x sub I over 2 times delta x, this is going to equal the sum I equals 1 to n, f of 16 over ni minus 8 over n times 16 over n. That equals a summation I equals 1 to n. And this is the stuff that's going to go in for x. Negative, remember it's x over 4, so I'm going to have 16 over ni minus 8 over n plus 4 times 16 over n. Let me simplify a little bit down here. If I take this 4 out, then I can cancel and make that a 2 and make that into a 4. So this is the sum I equals 1 to n, negative. I took out the 4 in the denominator, actually all the way. So what did it leave me with? It left me with 4 over n times I minus 2 over n. Summation I equals 1 to n. Multiply the 16 over n through, we end up with negative 64 over n squared times I plus 32 over n squared plus 64 over n squared over just n. And I can break it up into a series of summations. I equals 1 to n negative 64 over n squared times I plus 32 over n squared times I equals 1 to n, but this time it's just 1. And then finally this guy back here, we get plus 64 over n times the summation I equals 1 to n of 1 also. Alright, let's see what we end up with then. I have negative 64 over n squared times n plus 1 over 2 plus 32 over n squared times n plus 64 over n times n. And let's simplify where we can. I can take these out of here. I can take this out of here. I can take this and change it to a 32. And then like I did before, I can take this n and sneak it under n plus 1. So we have negative 32 times 1 plus 1 over n plus 32 over n plus 64. Then the integral from 0 to 16, what was our function? Negative x over 4 plus 4 dx is going to equal the limit as n goes to infinity. Let me find one of the earlier sums that I can use in here. I'm not going to use this one. I think I will do this one right here. And we see that equals that. This equals this last line here. That equals the limit as n goes to infinity. Negative 32 times 1 plus 1 over n plus 32 over n plus 64. And as before, the 1 over n goes to 0. The 32 over n goes to 0. I'm guessing the 32 over n was just collateral pieces. So I have negative 32 times 1 plus 0 plus 0 for the 32 over n plus 64. And we end up with the same answer as all the other ones. I'm going to end up with 32 again. Alright, the next video what I'll do is the same 3 methods on the quadratic we were working on. And then I'll do one last example of another quadratic that I pull off of an old test or something like that.